Okay, so now we know what is an MCNF problem and how an LP or IP formulation we may do for MCNF problems. Now, let's try to understand how MCNF problems can formulate many different kinds of problems. Okay, for some problems it's similar. We are sending something through a network, but for some other problems, I hope you may see that we are actually dealing with non-network flow problems. We are not sending items on the network, but those problems can be formulated as MCNF problems. Okay, so let's start. Below, we will show you many different well-known problems are just special cases of MCNF problems. Transportation, assignment, transshipment, maximum flow, and the shortest path. I'm not sure how many of them have been heard by you, okay, but for example, shortest path and the maximum flow, they will be discussed in your algorithms course. And for transportation and assignment, they are some very famous special problems studied in the operations research. Anyway, these are contained in chapters 8 and 9. We're going to give you some descriptions also. If a given problem can be formulated as one of the above, it is solved. Why? Because there are some special algorithms that is dedicated to solve each of these problems. Okay? What's interesting is that as these problems are special cases of MCNF, they are actually linear programming problems, right? So even though there are special algorithms, at least we know one thing. These problems can all be solved by the simplex method. No, that's all we need. We don't have time to talk about all those special algorithms for all of them. But those problems that we will introduce today, they can all be solved by the simplex method. So in the future, if you have a problem and you may formulate it as some of these problems, then you're done. Okay, so let's start with transportation problems. Suppose you own a firm and you have N factories that supply one product into M markets. Okay, N and M may be different. For each factory, you have a capacity Si, that's the maximum number of products you may produce in factory I. And for market J, there is a demand Dj, and that's the amount you should send into market J. Between factory I and market J, there is a route. So let's visualize this. Suppose at the left hand side, I draw these factories. Okay, 1, 2, 3, blah 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 up to N. You have several factories. And at the right hand side, there are several markets up to M. Then here we say there are routes between each factory I and the market J, like this. There is a route, 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 and so on. What do we do with routes? Routes are used to ship products. Okay, and for each route, there is a unit cost for shipping one unit from factory I to market J. That cost is called Cij. Okay, so in this sense, this transportation problem is similar to network flow problems, right? Because we are sending something on a network. Some parameters include Si, Dj, and Cij. So a problem is how to produce and ship products to fulfill all the demands while minimize the total cost. Okay, that's the issue. We ignore the production cost, we ignore the retailing cost. Here we only care about transportation costs. Suppose sum of capacity equals sum of demand. Okay, let's consider this situation first. In this case, all we need to do is to let Xij be the shipping quantity on arc Ij, Okay, this is just a natural way to formulate the problem as a network flow problem. And then this is just an MCNF problem with no arc capacity. Now, let's see why. First, we have factories. They are just supply nodes. Okay, we have markets. They are just demand nodes. The supply quantity at factories are SI, and the supply quantities at markets are negative DJ. Okay, here these guys are negative. Why? Because we are describing a transportation problem as an MCNF problem. In MCNF problems, all the nodes have a supply quantity, and if that quantity is negative, then this is a demand node. For markets, DJ is of course positive. Then when we translate it into an MCNF problem, it will become negative DJ. There is no transshipment nodes, and all the weights are unit transportation cost, CIJ. Okay, recognizing this simply tells us that a transportation problem is just an MCNF problem, right? Well, it's not very surprising. It's just some very special very special MCNF problems. There's no transshipment nodes, and arc capacity are unlimited. Okay. One problem that you must want to ask is, in many cases, our capacity must be larger than the demand, right? We have a lot of options to produce and sell to markets. What if we have this inequality? In this case, MCNF cannot be formulated directly because we require the sum of supply equals sum of demand. But this can be done. All we need to do is to create a virtual market labeled as market 0, whose demand is the difference between the total supply and the total demand. Okay. After we do so, we add some arcs with zero cost. Okay, with zero cost. So graphically, it will be like this. Again, we have some factories. We have some markets, and here we'd like to add node 0 or market 0. With that, we add several arcs from factory to this particular node. In this case, we say all the costs are 0. Why? We are going to send some products through this zero cost link if those products are not really produced. Okay? For node 1, I have a certain capacity. If some products are produced and sent to those physical markets, then there are some positive flows. If the capacity is not used out, then some products are sent through this virtual link. We are not really sending anything through here. We are just keeping those capacity unused. Okay? And of course, that does not incur any cost. So by doing so, we are able to handle this situation with excess supply. Another situation that we may want to handle is if we have production cost, how may we do that? In this case, the problem is simple. We simply update CIJ to CIJ plus CPI. CPI is the unit production cost of each factory. This may include a special case in which we have some outside suppliers. For example, total supply or total capacity may be smaller than the total demand, but we have some outside suppliers that sells products to us at a more expensive prices. Okay, and then because our capacity is not enough for fulfilling all the demands, we may buy something from outside suppliers, and they may be added into our factories. Okay, that's something we may do. Or if different markets have different unit retailing cost, then of course we can update Cij into CRI, and Cij plus CRI. That's something not a big deal. Okay, so that's transportation cost. Now let's talk about another problem, which is an assignment cost. So now it has nothing to do with products and routes. It's about jobs and workers. Suppose I have n jobs that should be given to n workers. An assignment must be one-to-one. That means one job is assigned to exactly one worker. You cannot assign two jobs to one worker. You cannot assign one job to two workers. In particular, a job cannot be split. Okay? The cost for worker J is to complete the cost for worker J to complete job I is Cij. So different people may have different preferences about jobs. I may do one job easily while I feel another job is very hard. That's possible. The different combination have a different cost. The problem is how to find the best way for assigning all those jobs. For this problem, it's actually a special case of transportation problem. Let's try to visualize it. So I have many jobs, 1, 2, and n. And I have many workers, 1, 2, and n. I'm simply asking how to construct this network. Okay? And it's not very surprising that here this is C11, here this is C12, and so on. And the interesting thing is about supply quantity and the demand quantity. In some sense, we are just sending jobs to workers. Okay, sending jobs to workers. So jobs are treated as factories, and workers are treated as market. What's important is that each factory produces exactly one item. The capacity is 1, and each market demands one item. Okay, a job cannot be duplicated, so there's only one item produced in each factory, and each worker can work on at most one job. So that's why the market demand are all 1. With that, then with the shipping cost as the cost for doing for worker J to do job I, we have Cij as the weight for arcs. Then this just becomes a special transportation problem, right? This is just a transportation problem in which the number of factories and the number of workers are the same, but their capacity and the demands are all 1. That's not a big deal. So what if there are fewer workers than jobs? What if I only have 5 workers? I only have 5 workers, but I have 10 jobs. In that case, the problem may be something like assign as many jobs as possible. Assign as many jobs as possible in the minimum cost. Or if I have fewer jobs than workers, okay, then I'm going to assign all the jobs, while some workers do not really have to work. In that case, we can still handle them, right? Just like what we do for transportation problems. We may add some artificial or virtual jobs or virtual workers to handle that situation. You may want to think about it by yourself. So for this problem, we actually can formulate it as an integer program. Let I and j be the set of factories or jobs or markets and workers respectively. So for the transportation problem, I are factories, j are markets. Then the problem is here. I want to minimize the total cost, subject to for each factory, the outgoing arcs, the total flows is exactly my supply quantity. And for all the demand nodes, the incoming flows is exactly my demand. And suppose I want it to be an integer program, I can set Xij to be z plus. For an assignment problem, here is very clear why an assignment problem is a special case of transportation problem. It's just that the supply quantity are all 1, the demand quantities are all 1. And what's interesting here is that xij is now a 0, 1 variable. You can still say that xij are integers, but of course they will just be 0 or 1. We are selecting some arcs, and those selected arcs means we assign one job to a particular worker. Here, suppose we want to show that it's a totally unimodular matrix of the coefficient matrix. Of course they are, because they are special cases of MCNF. All we need to do is to say this is the first group and this is the second group. Then we're done. What's interesting here is that relaxing the integer constraint is not a big deal for transportation, but it's very important for assignment problem. Let me elaborate about it. For a transportation problem like this, we are deciding flow quantities. Okay, flow quantities. And when the problem size is large, problem scale is large, we know it doesn't matter to relax the integer constraints into fractional numbers, okay? Because rounding doesn't make a big deal. But for an assignment problem with binary variables, typically we cannot afford to relax binary variables, right? For typical problems, relaxing binary variables cannot generate an optimal solution. For example, knapsack. For knapsack problem, all the variables are binary variables, and we cannot relax them into integers. That's going to change the optimal solution. But for assignment problem, because it is totally unimodular, we can relax xij to be fractional numbers, and then we will still get integer solutions. So to solve this problem, we simply solve an linear program, and then we will get integers optimal solution. So now you can probably get more ideas about why we really care about total unimodularity. At least it helps us to really solve the assignment problem. Okay, if the last problem we want to introduce in this video is transshipment problems. So it's very simple. If there are transshipment nodes in a transportation problem, then the problem becomes a transshipment problem. So for transshipment, transportation, and assignment, and MCNF, we have this hierarchy or reduction map. The general MCNF problem is here, minimizing C transpose X, subject to those flow balancing constraints, capacity constraints, and non-negativity constraints. If an NCNF problem has unlimited capacity, it becomes a transshipment problem. If there is no transshipment nodes, that means all the BI are positive or negative, then it's a transportation problem. If all the supply and the demand quantities are 1 or negative 1, then it becomes an assignment problem. So one is a special case of the other one. That's the hierarchy for these problems. In the next video, we will introduce 2 more problems and show you a more complete graph. Thank you.